Here we go. Good afternoon, ladies and gentlemen. Hello, my name is Abilio. Together with Barry White and Andrew G, we are hosting the second session of our IBM system back to school. So thanks for coming. Thanks for passing by, and I hope you enjoy it. So what is all this series about? So the idea is to, well, you can go back, don't need to rush. Just one slide. So thank you. The idea of this series is just to try to fulfill the gap that we have in the first half at IBM, as we don't have those worldwide events that we host usually in Orlando, Vegas, Atlantic City, Sydney, Melbourne. So the technical team here in New Zealand decided to do in our time zone a small version of it. So it is a series of eight sessions. This is the second one. So this is basically what we are here now. Who we are. So no, okay, go next. So we had a session last Wednesday with Barry White, ATS from IBM. This is myself, the second name here, Abilio. I will be doing the last two sessions on these tech series about Scale, Discover, and Spectrum Tech Plus. We have Pat Alton, which is the System Z specialist, which is our mainframe offering. And today we have the honor of having Andrew G on board. I asked him to keep his mini bio as small as possible. I said just the last 30 years of experience, please, Andrew, but he didn't listen. So he's a very experienced guy. So we're glad to have him on board on the team and having this session today. Moving on. Okay, so as I said, last week we had the why IBM Flash Systems. We already have the replay available on YouTube, on Barry White's blog as well. Today we will have the session called why IBM Power System, which is presenting to you guys another form of doing compute, in our perspective, a better form of doing compute. And Andrew will give us the details. And Andrew will stay with us next week as well, talking about a specific use case of Power Systems for SAP HANA platform. And after that, we will have troubleshooting performance for storage with Barry White. Your AI needs an infrastructure agenda, which is basically another topic covered by another use case covered by Power Systems with Andrew as well. And I will be disturbing him during the session to talk a bit about storage while he speaks about compute, because it is an infrastructure agenda. And then we go to Linux One as a scale up type of thing compared to x86 compute service. And then the last two is about protecting data and managing data with me. So stay tuned. All the material is available on YouTube and on our public box folder, which is already published by my LinkedIn post and Barry's post and also Andrew G's post, if I'm not wrong. So we are not hiding any information. All the information can be set there. The only observation is the video is too long, so I recommend you to watch it on YouTube instead of downloading almost 1 gigabyte of files. But that's just a recommendation. It's free to download as well. Yeah, and we can move on. Okay.
Hello. So I guess I'll take over.
Yeah, so I was here and I disappear. Andrew G, the stage is yours.
Thank you, Abilio, and good evening, good afternoon, good morning to our attendees. I trust you're all managing to keep well and safe and socially separate, as it were, at the moment. Things aren't looking quite so bad over here at the moment, so we're doing New Zealand's doing pretty well. So, why IBM Power? First question, I'd like to try and keep it a little bit interactive. I can't see the chat, but feel free to chat in there, ask questions and answers, and we'll bring those through again at the end. But I don't want to be like a teacher saying, how many colors do we say in the rainbow? Anyone? I don't want to do that. I want you to respond if I ask you a question. Feel free, hop into the chat. So, Abito's just put up our first poll and see if we know what power stands for on here. So I do, so I'll get rid of that. And so if you guys come answer and see what you think. And all being well, I should be able to give you that. Performance optimization with enhanced risk. So it's actually an embedded acronym with the reduced instruction set computing. So what we're going to do is spend quite a bit of time on some of the hardware differences, and then we'll go into the end with virtualization and use cases. So the power roadmap, it started way back in the origins of it started way back in 1974 when the Commonwealth Games were here in New Zealand, and New Zealand got 9 gold medals, and India, I think, got 4, and Australia got 29, but we'll forgive them. And IBM started working on a telephony switching system, so it didn't have to do much. And what they wanted to do was to make the complex instructions all work at the same time and be controlled by one instruction, and that became eventually what was known as RISC, reduced instruction set computing. So we had multiple iterations of that. We never had a power 1, we just had power, and then power 2, 3, 4, etc. So we're going to kick in here at power 5 in 2004, and this was the first one that brought in symmetric multi-threading. So we were able to do SMT2. So we could do 2 things at the same time. We just call it SMT2. x86 calls it hyper-threading. It's really hyped this up a bit. We're very good at that in the IT industry. 2004, you see we've got 276 million transistors on that. Now, Moore's law says that we double the density of the transistors in an integrated circuit or complex circuit roughly every 2 years. And we kind of almost do in most of these steps, because you see what we typically have is around about a 3-year window, a 3-year cycle between processor generations. And sometimes it slips out to 4, sometimes we kick it in a wee bit. But so 2004, we had Power 5, 2006, nothing. Power 6 came along in 2007, and it was still SMT2, but we brought a few extra things in there, instruction retry, so we could actually improve the reliability of the systems, and we got higher frequencies. This was actually the result of a program where we tried to bring the Z mainframe, as well as the IBM AS400 as it was in its day, and the RS6000, they came together in Power 4. What we tried to do in Power 6 was to bring the Z mainframe in, but that didn't happen, so they stayed out on their own, and the Z10 came out. And the Power 6 processors, you will see, went from 3 to 5 gigahertz in performance. So for single-threaded and dual-threaded applications, they were incredibly quick. When we went to Power 7, in 2010 and 12, there were two different versions. We had a wee tick in 2012. Although it's slower in clock speed, and it doesn't say what it is on here, it actually did more work because we actually could SMT4, so we could do 4 threads, 4 instructions at a time. We increased our reliability, and we did a few other things that bring the L3 cache onto the on chip. So from 2010 to 2014, because of that tick, Power 8 came out, and you can see that we've gone from 2 billion transistors to 4 billion transistors. So it's kind of Mr. Moore's, but we also made it smaller. We came down from 45 nanometer to 32 nanometer to 22. And we've done more with reliability again. And eventually in 2017, so this little baby is 3 years old now. we have SMT8. Well, we had SMT8 in Power 8, and we've got SMT8 in Power 9. Power 10 originally was due for release this year, but with the things that are happening at the moment, I'm pretty sure we'll see that in 2021. I've got no information on what's happening next. IBM, we have statements of direction, and then we have little caveats next, asterisks. So the key thing is performance optimization with enhanced risk, and that's where I want to spend a little bit of our time. And that you can see there is the Power 9 processor, and I'll just enlarge it a bit. Now, what does it look like to you? What do you see? I mean, feel free to hop in on the chat. I see 1920s skyline, old sort of almost Art Deco 1940s New York skyline. I see 12 buildings, some upside down.
It looks to me as a Rorschach test, isn't it?
If the people do respond, we won't take them as a Rorschach test, no. But it's actually it's fun. What we actually have, I think this is really quite pretty. I may be quite sad in that respect, but do you also notice the symmetry of the 12 large modules? They're sort of replicated side to side. So if I was looking at this and I see 12 large blocks with a big bit of electronics down the middle, then I'd think this was a 12-way processor. But is it? This is what it really is. We actually break it down into each of those large blobs is actually 2 cores with 4 threads. So this one chip design can give us 12 cores with 8 threads, or in this case, 24 cores with 4 threads. And I'll just show you, this is how we work with this thing. So you can see why I think it's pretty when you see Power 8, its predecessor on the left-hand side there. So we start off with a 64-bit slice, and we put 2 of those slices together, and we call it a super slice. And 2 super slices together gives us a core with 4 threads. We put 4 of those threads together, 4 super slices together, and we have a Power 9 SMT8 core. So why do we need SMT8 and why do we need SMT4? This is our product range. The mission critical workloads with the purple looking color is our normal business highly available systems. The right hand side in blue are our big data workloads, AI workloads, machine learning. And what we find is they like cores. They don't really like threads that much, so they don't need very many. So what we do is we put 20, or well, we could do 24. We put 20 cores on a chip in each of those. And so a single 2U high box has got 40 processors in there, and each of those processors can do 4 threads. Whereas on the left-hand side, the transactional systems, shall we say, tend to do more random type workloads, and we don't necessarily want everything to finish at the same time like you do when you're doing big data workloads and AI workloads. So these are 8 thread boxes. So with that same die, theoretically, electronically, we could turn cores on and off. We could just manufacture them. So we don't have to make a different core for multiple different systems. One of the conventions of IBM is that we confuse our machine naming. So when Power 5 came out, we had models such as the 520, the 550, 570, 580, 595s, etc. And so the premise was that the bigger the number, the more powerful it was. And it just happened to be quite good that they were Power 5 520s. That was good. So we brought Power 6 out, and we had 520s, 550s, 560s, etc. We didn't change the numbering convention. Power 7, we did. And again, we carried through with the 7, 10, 30, 40, 50, etc. And then finally, some bright spark at Power 8 decided we could actually make some meaning out of this. And so we changed the numbering convention. So we have an A, XYZ numbering convention. The A, the first character, outlines the offering that the machine's going to go for. So if it's L or LC, it was a Linux cluster. The H we tend to use for SAP HANA. AC is for accelerated computer, and now we have a new one, IC, for inference or inference cloud, inference computing. S for scale out, and E for enterprise scale up. Excuse me. So we typically use scale out and enterprise in our world, so S or E. Now this is only for scale out. Enterprise is still using the bigger number, the more powerful it is. So we're not totally logical. So when we brought out the 7XX, it was a power 7. We brought out the 8XX, it's a power 8. We brought out the 9XX. What are we going to do when we go to 10? So that's a conundrum. I think we've got a poll question. We'll leave that running for a while. What should we do? We never had a 0. We never really had a 1. But do we use 0? Do we use A? Do we use X? Right, the Roman numeral for 10, or we could do 10 and go from a BMW to a Peugeot with the SUV numbering convention. So yeah, drop it into chat. If your video fires up the poll, we'll see what you think we should do. We can feed it back to the company. They'll probably ignore us, but it'll be interesting to see how you feel we should go with this generation and what's to come. The second digit is the number of sockets in the machine. So a 924 has 2 sockets and a 914 has 1 socket. And finally, the Z refers to the number of U it takes up in a rack. Now we do have one machine, which is the 914, which can be purchased in a tower or standalone model. It's just slightly different, but it is available. So if we were to say, for example, we bought out, hypothetically, an S914, what would it have? So the S scale out, 9 power 9, 1 U high. No, don't know, one socket and 4 U high, right? So that's a big beast with not a lot of processing power. So we talked about power optimization. So what do we optimize? What do we spend our time on? So a transaction is made up of many components. We access the data, we do the I/O, we get it either from out on disk, which is really, really slow. Then it comes into the processor, down the PCI bus, which is faster. If it's in memory, we move it from the memory to the processor, which is really fast. And then, of course, the processing time is the fastest part. And then we output it all again, so we slow it down. So if we look at it here, I've tried to do a graphical representation of what we have. So the top line is our normal transaction. Now, back in 1960s, a period of discovery and innovation and enlightenment, and some of those enlightened discoveries are still illegal 60 years later. One person came up with a law, and his name was Gene Amdahl, and he was an IBM architect in the System 360. And he was working more on parallelization. And Gene said effectively that if I have 20 steps, 20 objects to do, and the slowest one is only single-threaded and it takes an hour, my total time for my transaction cannot be less than an hour. So he was advocating putting more and more processors into a thing, into a system. So what we're going to do here is just show you, if we have a transaction, and for many, many years we had processor wars. You know, we're running at 230, DEC Alpha bought out a 500 megahertz, right, processor. Now, oof, that was off the planet to us. So we did twice the processing speed, but look at the effect on the transaction time. It's not a lot. And if we make it twice as fast again, right, it's even less of a gain, because really we've only 3 times as fast now, not 4. So we've already seen a diminishing rate of return just by going twice and twice on the fastest bit. It's really, really slow. So look at the gain we can make if we go twice as fast on the slow parts, like the I/O bringing it into the processor or the I/O putting it out. So we'll have a wee look at some of these things. So our Power 9 processor has around about 1 terabyte of bandwidth to the processor. Within the processor itself, it's got around about 7 terabytes of bandwidth. It's quite powerful. We have memory bandwidth, and we have a couple of different sorts, obviously. So our scale-out servers are doing 170 gigs per socket. An Intel Skylake, I think, which is the most likely comparison we would have, because these have been out for 3 years, does 128 gigs a second. So our power processor has 1.3 times the bandwidth of an Intel processor. Now, we also use industry standard RDIMMs, and we can put 4 terabytes in a two-socket system versus 3 terabytes in a two-socket system from the x86 world. So we have 1.3 times the capacity of an Intel platform or an AMD platform, x86. Does that matter, 1.3? Well, yes, it does. It adds up. So we don't need 2 servers to go over 3 terabytes. And in our talk next week on SAP HANA, you will find that a good percentage of HANA databases around the world are between 2 and 4 terabytes, maybe 80% to 2, and then a slightly smaller percentage in the 4. We can do that on one box. When I sold Intel, I'd have to sell a 3 terabyte server, and then I'd have to bolt another one on to do anything greater. Because remember, although we're talking about HANA here, the amount of RAM in the box is generally double the size of your HANA database. So if I've only got a 3 terabyte system, I can only do a 1.5 terabyte HANA database really. So we can actually do 2. So there's a good added value from the IBM platform. In our scale-up servers, we do 230 gigs per socket compared to Intel's 128 gigs a second. So we've got 1.8 times the bandwidth. We can move that much more from the processor and memory back and forth. In a 950, that's a 4-socket box. That gives us 920 gigs a second for memory bandwidth. Those machines also use a different technology. We don't use the industry standard RDIMMs in those. We use what we call buffered memory. And these have got enhanced performance, obviously, as you can see. But we also have cyclic redundancy checks. We have chip kill, so we have spare memory modules on the memory boards. And excuse me. So if a memory module plays up, we can just remove it from the system, and there's still enough memory on there. And we also do dynamic lane sparing, talking out to the caches. So if we have problems with a lane, we have spare lanes in there. So these are why they're called E. These are enterprise servers, enterprise reliability, and we'll come on to that later. So at 4 terabytes a socket versus 1.5 terabytes a socket in x86, and we could theoretically go to 8 terabytes a socket, we have 2.6 times the capacity per socket.
Hey, Andrew,
yep.
Can we buy that if the memory is industry standard?
Can you buy, yes, this is always a question. Can I put other people's memory into our systems? We used to, we found some memory providers do, but I think what the question is more these days, Abilio, is there's a new kind of memory that's come out. And Barry referred to it last week as storage class memory. And we know this is the Intel Optane memory. And it's persistent. So the data that's written into it stays there. And on the Intel system, we can, I think they have 12 lanes, and they could, on a 2-socket system, they could put 6 of those in. They could be 256 gig, or they could be 512 gig. They're actually quite large, but they are really expensive. And what the difference is that they are faster than getting data in from storage, but they are slower than DRAM. But they're sitting on the DRAM bus. So you're actually gaining capacity, you're getting persistence, but it's not quite as fast as DRAM. Oh, and if you want to use it, you have to buy Cascade Lake, is it whatever the current version is. You have to change your Intel structure to take advantage of this. It's only in the very latest systems. Whereas IBM has a thing called virtual persistent memory. We released that at no charge. So everybody who's got a Power 9 system, upgrade to firmware 940. There are some others, little gotchas. One is you have to have the appropriate level of the hardware management console, and you have to be running, and this is more of an SAP thing, you'd probably have to be running SLES 15. Not sure about the Red Hat version. And it's free. So we've given you virtual persistent memory. You don't have to buy another module and put it into our system. We actually say this is there all the time, and it will survive a partition being booted, for example. And why is it better than putting Optane in? Because it works at DRAM speed. Optane's slower, so if you say, oh, it'll shut down, it'll boot faster. Well, it'll certainly boot faster, but it'll shut down slower because the throughput speed of the persistent memory module is around about 10 times that, sorry, it's 10 times worse than a DRAM module. So it could actually take you longer to shut a system down with persistent memory modules in it, whereas shutting our system down, it works at DRAM speed. Bringing our system up, it works at DRAM speed, much faster. So we've had a system which was 8 terabytes, HANA, so it's a 4 terabyte database, and they increased the speed from 40 minutes, I think it was, to 4 or something. I'll find, if I can't remember, I should be able to remember what that delta was. But you get that for free. So if you're running SAP HANA, I'd certainly encourage you and your clients to look at virtual PMEM. We have as for the business partners, we have a site on IBM called Seismic, and we can provide, there's a primer on there or primer paper and describing how it works and what you need to do within your system to make it work. But we have that for free. One of the things that, this is the fastest bit. So I just want to go through these things that Albedo's putting up poll questions, but the first one's coming through again. We need the second or third one. So the processor speeds.
Sorry.
It's okay. It's okay. No problem at all. So the processor speeds we show, and this is typical of most infrastructures. The more cores they are, the less speed they have. But as you can see here on a 924 8-core, which is our fastest processor. So if you have an old application that's single-threaded, it not able to take advantage of hyperthreading or SMT8, as we would say, then this is perhaps the machine you should look at. If you need the maximum throughput, then by all means, go 12-core. You'll only lose a little bit at the maximum, but a little bit less at the bottom end as well. So you S822s and 922s, so you can see from the last digit, these are 2U high versus 4U high. So we run these a little slower. It helps with the cooling in the platform. And again, 8 cores and 12 cores. So not a lot of difference. The Linux one is appreciably slower at 2.7 to 3.8. And I'm just having fun and games with my mouse here. Thank you. We have the processor interconnects. Obviously, we have 2 cores or 2 sockets. So sorry, 2 sockets in our system, and we have 4 sockets in our nodes and our enterprise systems. How do we hook those processors together? Well, we've got 2 what we call processor cross-bus interconnects on the S's, and we've got 6 of them effectively on the 980s, right? That's within the node. And I've said here, go and check Intel's UPI speed out and see what we're doing. We've got 216 gig per second. Intel tends to talk in like transactions, GTs, whatever it is. But between our nodes on the SMT8, my goodness, on the 980s, we have 1.5 terabytes of bandwidth for the processors to communicate between the drawers. or nodes as we call them. So this is really enterprise performance we've got up there. Why do we show a range of processor speeds? Well, it comes down to we have several modes that we can run it in. We have the first node which is on here basically is a static power saver mode. So if you're a small organization that has a power system and you're not really using it on the weekend, you can put this into static power saver mode and it will just tick over very, very slowly using the minimum performance that it can. We have static nominal mode. So it just sits there at idling and drops, if it's idling, it drops the power down. Most of our systems, bar one, ship automatically in the maximum performance mode. So on these ones, the workloads run at the highest frequency possible. It runs greater than what we would call the turbo. So our nominal speed would be the lower of the two, say the 3.4, and the ultra would be the 3.9 or the 4. And turbo is kind of in the middle. So what we do by default, we ship them with this mode. You can, if you want to, change it back to dynamic performance. So it would run at the nominal processing speed. Now, you might want to do that if you wanted to be energy conscious. You're green. We've got the option of doing that. And if you've got a light workload or many idle cores, this is good. You're not pushing the system hard. And obviously, the harder you push a system, and the hotter it runs, and of course the fans go. So we ship dynamic performance turned on the 914 by default. So the 914, if you remember me earlier saying, has a tower package because it can sit in an office. But if you were to change that into maximum performance node, those fans would spin up and it would become quite a hindrance to the comfort in the office. So we manage the draw. Your customers have the option of controlling their power consumption. So the I/O bandwidth, this is another one of those slow, right? We're starting on the slow red stops. What can we do? So we'll start with CAPI, Coherent Accelerated Processor Interface. We love acronyms. These are interfaces for accelerated cards, GPUs or field programmable gate arrays. Can come in over the CAPI interface. Now, our CAPI interface now runs CAPI 2, and runs over our PCI, which is PCI 3 and 4 in the lower machines, and 4 almost exclusive, well, it is exclusively in the enterprise boxes. We have PCI 4 I/O, PCIe 4, sorry. So traditional accelerators access the system memory via the PCI bus, and then via the processor, and then to the memory, which is slow. So CAPI makes the FPGA or GPU appear to the processor, and from a memory access point, so they can actually share memory that the processor is actually working on. It's much faster. We did actually have CAPI attached storage, so we can go straight out from the CAPI card out to an FS900, I think it was in the day. And then we have what we call Open CAPI. And this is the newer technology that's coming out, and we've seen that on the AC922s and the IC922s. We have 25 gig bricks and 6 per socket, and that gives us 300 gigs bidirectional transfer GPU to CPU. Right? And we also have, because we have these links on it, we can also do GPU to GPU, and I've done a typo there. So the 200 is GPU to GPU. So there's a link between the two, not to the CPU. This is considerably faster than an Intel system would work or an x86 system work. NVLink for GPUs. We have in the AC922, we're using the Tesla V100s, and in the AC922, we're using the T4s, I think it is, which are PCI based. ASICs to come. So other than the CAPI, which we use for FPGAs, and it's field programmable, i.e. you can change it, an ASIC is generally hard-coded to do a specific job. So you may see those come for Power 9, probably Power 10. Most of our competition still use PCI Gen 3. So PCIe Gen 4 is 2 times faster. We've got 192 gigs a second across 48 lanes. It's in every system that we make. Even our smallest 914 has got 2 PCIe Gen 4 slots in it. So we're future-proofing the servers for higher bandwidth. If somebody brings out a 200 gig network or something like that, we've got a future-proof there already. Our InfiniBand adapters drop in and they use CAPI, if I remember rightly, as well. So we've got some technology that's using it. What we've also just done is release an NVMe adapter of storage, and these plug into the PCI 3, PCI 4 slots on the I/O component. So even in a small system like a 922, we could drop 4 in realistically. You could put 5 in, but 4 realistically because it has no data protection. And so you need to use an OS mirroring or software RAID or something, but these are 1.6, 3.2, or 6.4 terabytes. So a pair of those, you have to buy a pair to mirror them. It's really good, but wait, there's more. So until the 30th of June, just check your geography, but we're offering a 2-for-1. So for the second quarter this year, and I knew I'd forget to do it, and I even had it change the color on the memory when I was talking about the memory modules. We've actually got an offer for Q2 as well in the 32 gigabyte options. We are doing 2-for-1 of those as well. I believe it's up to 512 in the 922. So if you are going to, you'd buy 256 and get 512, or you buy you take 512 and only pay for 256. And in the 924, I believe it's a terabyte. So we would charge you for only 512. Oh, and another thing about the memory subsystem as well. Maximum bandwidth is obtained by half filling the slots. So if you can, use 8 of the 16 slots per socket. Because when you go, we typically run it, depending which memory module, 2666 or 2400. But if you go into that second bank, we'll slow it down to 2133. So you've got more memory, and the maximum bandwidth is achieved with the slots half full. So if you're going for a single socket, then fill it up with the 64 gigs, and you get your half terabyte away. So yep, so that's it. So they have a memory offer, and we also have an offer on the NVMe's until the end of June. So if you've got anything that's basically a standalone system, you could use this with HANA. You could put the drives inside. So anything with standalone system, you still need to, they are bootable, but various requirements still need to be met. Like you do still, unfortunately, still need to put a backplane in, even if you haven't got one. But you don't need to put the enhanced backplane in with the extra SAS controllers or anything. You can get this. Or what I would do potentially is drop a split backplane in with minimal disks for BIOS. And then I would present these to multiple LPARs if I wanted to. So yeah, good luck on working with those. They are really quite exciting. So here's a typical marketing slide that we have. All of these statements are true, but they don't resemble any one specific box. So if we start at the left, I said we have a terabyte of bandwidth into the chip. We've got 7 terabytes of bandwidth on the chip. This is true. We've got the first chip with PCIe. Yes, it's true. 8 billion transistors. That's more than there are people on the planet. We have more than 24 billion VIAs, and that's the vertical connections between the 17 layers. So if everybody on Earth held hands with an interconnect, we'd have less than a third of the interconnections that are capable on this system. A 4 gigahertz peak frequency, yes, we do that, but we do that in an S94 8 socket. So they're all true. This is the sort of marketing information you see. Again, all true, and we've got things to back this up. So what we've got is 2
Hey, Andrew.
Yeah.
Can I just add a question here? What kind of business benefits of all the technology that we have so far compared to these numbers?
Okay, well, we'll go through this one, and so if we can get twice the performance on a core than we can over an x86 box, then we can do the same amount of work with half the cores, or more work with the same number of cores. So this comes down to how many physical systems do we need, and the fact that we can scale up to 192 cores in the enterprise system gives us a huge amount of capability with multiple virtual machines inside there. Same again, more RAM per socket. The 2.6 is the larger variant, which is the 4 terabytes per socket in the E980 versus an Intel platform. So again, more bandwidth, more RAM per socket. We need fewer sockets to have the same amount of memory. So again, if you're an in-memory database, if you're using DB2 or any of the other in-memory databases, MongoDB or HANA or whatever you want to do, the more memory per socket is better. And again, we have 1.8 times the memory bandwidth again on the enterprise system, and 1.3 times on the smaller systems. And with the NVLink, we have 5.6 times the CPU to accelerator bandwidth. And I think what we'll see is this will increase potentially to 9 times with the next generation accelerators and PCIe 4, and to come is NVLink 3. So we've got lots of things to come, and we can see that sort of stuff. So what I talked about earlier in the processors and the memory, another business value that it gives us is reliability. Now, IBM systems have always been phenomenally reliable. And one item that our partners should have in their toolkit, and IBMers should have in their toolkit, is the ITIC reports. 88% of the customers that they surveyed say they now require 99.99% uptime for mission critical systems. That's up from 83% last year. For the 12th straight year with the 2020 report, which is due out shortly, but they put, if you go to the ITIC site, you'll see the blog, and they put the wee teasers up the front there. So for the 12th year straight, IBM mainframe and power systems have achieved the highest rankings. We are the most reliable hardware and OS solution there is out there. 88% of the customers they surveyed said they estimate an hour of their downtime is greater than or equal to $300,000 an hour. For some reason, that's $4,998 a minute, not $5,000. But that's also up from 86%. So 88% say that an hour of downtime is $300,000. So IBM Power 8 and Power 9 systems exhibited less than 2 minutes of unplanned system downtime per system last year. So money lost, shall we say, would be around about $10,000 by that 2 minutes. Some name brand servers, x86, exhibited 26 minutes per server unexpected downtime. That's $130,000 a year for a single server in potential lost business. We're still the white boxes, 53 minutes per server, $264,000. So when your customer says, my x86 box, my total cost of acquisition is lower with an Intel platform or an AMD platform, then you need to point these numbers out to them, and you say, this is what it's going to cost your system, your business, if they're not available. Now, of the people that were left, really the 88% said it was 300,000. 34% have actually said it's over $1 million an hour. So these guys need that enterprise reliability. They need that memory buffering capability, the CRCs, the chip kills, the processor deallocation that we can do. So we can dynamically turn a processor off in our enterprise systems. If we start getting too many temporary errors, we can actually stop the host from talking to it, evacuate all the threads off it, and then shut that processor down until there's an outage time, a planned outage, when we can actually replace that processor module if we need to. So these are some of the many features that we have. If you haven't seen that ITIC report, as I said, 2019 is the last one I've seen physically. 2020 is coming. It's a teaser. Then drop us a line, and we'll get it out to you. And here's some of those RAS features we were talking about earlier. So yes, we can move a partition while it's live. Well, yeah, you can with VMware as well. Live application mobility. Can we move the application live? Yes, we can. Not quite so easy on x86. Partition available priority. Yeah, we can do that. Yeah, we can say these partitions are more available, so if anything's coming up in a certain order, we can do that. OS independent first failure data capture. So when something goes wrong the first time, we actually capture it, and we make it relatively easy to analyze. Yes, you can do that in x86 with an MCA recovery process, but I've watched a YouTube video of them doing that in VMware, and it is rather long-winded to find out what it is. Memory keys, yes, we have that as well. Processor, we can retry an instruction. So if we catch an instruction before it completes and we think, hey, this isn't right, we can actually retry that instruction again rather than having it fail or corrupt data. We can fire it off to an alternate processor if we want to. As I said, we can dynamically deallocate a processor if one starts to exhibit too many intermittent errors. And we have dynamic processor sparing, so we can actually fire up. If you've got dark resources, you could bring another one in. Memory. And see, no, for x86, they don't have those features at all. So this is what the IBM system gives you. It gives you your reliability. And I'll come back to that at the end here with chip kill. Yeah, some vendors do have chip kill. We have a double memory failure. Yeah, we do selective memory mirroring. Now, what we mean by that is, on an Intel system, you can say, yes, I will mirror my memory, and basically you've got twice as much memory in there. So when you mirror your memory, you actually cause a performance degradation on your system as well. What we're doing with selective memory mirroring is saying on our enterprise systems, our E models, is we can mirror the hypervisor memory. So the hypervisor on the system is what controls everything, and we can actually mirror that just in case you have a very rare occurrence where it dies. And we've got I/O, better error handling on I/Os for PCI buses, etc. So let's do a wee talk on virtualization and workloads. We've spent quite a lot of time at the bottom of this stack talking about the processors and the memory and the infrastructure, but it's not just about hardware design. It's about the whole stack, the software that we've put in there, and the partnerships that we have. And I just want to cover some of that, but I just want to quickly go over virtualization. It's a little bit messy, this, but I'm trying to try and introduce, if you haven't got your head around virtualization on the power systems. We have a managed system, which may consist of multiple logical partitions, and it may have a VIO, via a BIOS, a virtual I/O server. That isn't compulsory, but if you want to share I/O, like Ethernet cards or fiber channel cards, you want multiple LPARs to share them, then you need a VIO. There's nothing wrong with having a discrete physical adapter per LPAR, and you could use the VIO. So if you wanted fiber channel cards, you could have a physical card associated with the LPAR, but you could use the Ethernet virtually. So these are the components that make up our systems: the CPUs, the memory, the hypervisor, and the flexible service processor is what our management console connects to via private Ethernet connection. So a little bit clunky of a diagram, but what we've got here in partitions across the top, we have 11 partitions on this system, and we can see that we've got processors in partition number 1, for example. We've got processors, we've got memory, and we've got adapters, and it has its own external disk. It's not a problem at all. Partition number 2, that was a BIOS server as well. So partition number 2 is an AIX partition. It doesn't have as many processors or memory, and it also has its own adapters. Partition 3 can be Linux. Partition 4, now you see what we've got here, the P's are all in one line across partition 4, 5, 6 through to 11. What does that mean? Well, we can actually have the concept of a shared processor pool. And what we do with a system in a shared processor pool is we can say, sorry, I've just got a problem here. We can say that an LPAR is allowed to use from 0.05 of a processor, that's the smallest LPAR we can make, up to the maximum number. If we uncap it, it would use as much as it can. That can cause software licensing issues. If you've got a pool of 12 or 20 in your system and you say, oh, that LPAR is uncapped, and if it grows, it will just go. So what we can do is we can share a pool of processors, and we can actually control our licensing as well. So for example, I have a client that wants to run an IBM I workload, and we charge by the core for the operating system on that. And so they didn't want to go more than 4, but they had multiple partitions. And so we said, okay, what we'll do is we'll carve you a shared pool of just 4 cores off. And then we'll put all of your LPARs in there and say, right, you can all have 0.1 to 4. They can't ever exceed the licensing requirement because there's only 4 physical processors there. But they can take cycles off each other. This one's, and you can assign an order of priority or highest precedence. So this LPAR is more important than another. So we can actually right size our systems for our clients. We don't just say, well, here's a 2-socket box with 256 gig of RAM in it, go for it, right? And then with your VMs. So with VMs as well, if you want to make sure you're getting the best performance, you might want to do a thing called memory affinity or processor affinity. So the VMware may say, I want to only use the memory that's physically associated with this physical processor. Well, if you do that with VMware, if my memory corrects me, is correct, you have to do it at a minimum of half a socket. So half the cores have to go and be tied to that VM, and then it's 1, 2, 4. You have to do it in whole sockets. So we don't have to do that. We can start as low as a 20th of a core, so 0.05, and then we can increase our cores up to well, as many as there are in the system, but we can increase them in increments of 100th. So we can have 4.31 if you want. Of course, we can actually, and it's about right sizing. So what we're showing here is we can have dedicated partitions. So these cores are, this virtual processor number 30 is actually a real processor, all 8 threads and everything, and the whole 100% performance is available in this. And we have 4 cores. What we've done in this one, LPAR 2, we've said I want to give it 1 virtual processor, but I want it to have 0.3 of the performance of the entire core. And so we do that, and of course all of that 30% comes off the 1 core. This one over here, we said I want 3 virtual processors. And so what I do is I get a 10th of and again at 0.3, so I get a 10th from each of the 3 virtual processors on there. So this is what we do. So virtualization's making one server look like many. Our scale-up servers are the best way forward with your systems. We have scale-out, so if you want, you can do multiple physical servers, but scaling up is always better. If I just whip back a page, we have this virtual Ethernet here as well. So the LPARs within a system can talk down the system backplane to each other. It doesn't have to leave the Ethernet adapter, go to your switch and come all the way back like you did when you get converged infrastructure on a lot of other systems. You physically have to go out to the port, go through the switch and come back down again. Our guys can talk at the bottom. And what have we got? Use cases, right. So because we've got multiple LPARs I've just gone through with you, you can see that we can simultaneously run AIX, which is IBM's Unix, and it's certified for Oracle now with live updates as well. IBM I, our integrated operating system and database, DB2. Linux, of course, Red Hat, SUSE, Ubuntu, Red Hat OpenShift, Kubernetes, Ansible. We have IBM Cloud Paks, a software. Part of that whole stack is a software, data applications, etc. And we can find that with that, it can be significantly cheaper to run a Cloud Pak on an IBM Power System than in AWS or Azure, for example. SAP R3, the traditional model, and HANA Obviously, very, very common on our platforms. SAP has actually introduced Power into its HANA Enterprise Cloud solution now. So they like it so much and they really go with Power 9. Oracle, yes, we can run that. JD Edwards, Oracle applications, absolutely. And the SAS Institute, if you're doing a lot of analytics, you may hear of this at 9.4 or the new version Bayer. They've decided that Power 9 has a lot of benefits to them, and they're really enamored with us, and we're starting to get the relationship working with the SAS Institute again. So we're just about out of time. I've just about got there, but Power Systems. So we have them on premises, in the cloud or hybrid. Now we can actually put IBM Power Systems via a thing called Power Virtual System, our virtual server on the cloud. There are some gotchas with the cloud, not necessarily with the power side, but with x86. And remember me saying we can do twice as much with half as many cores, etc. So we support twice the number of containers per core as an x86 platform does. Now that matters because you don't need as many virtual machines or on the cloud. We have twice the performance, but multiple benchmarks attest to this as well. So AWS says that if hyperthreading is turned on, one virtual processor is one thread. Azure says the same thing. So one virtual processor is one thread. And this was taken from an Oracle licensing document. If hyperthreading is turned on, a virtual processor is a thread. And Power, as you saw when we dedicate them, one virtual processor is a processor. You've got 100% of that, and those 8 threads are available to you. So that can make a huge difference in cloud-based application licensing. Potentially in the order of 6 times cheaper to run the IBM Cloud Packs on IBM Power Systems. So in summary, there you go. The various models that we've gone through, our enterprise systems and our mission-critical data-intensive workloads. And then we have our big system workloads, which use the 4-thread SMTs. So I hope this has been of value to you. I will invite you back for next week to boost your SAP HANA with IBM Power. And I'll leave you with this quote that I got from a business partner in Australia. The more I learn about SAP HANA integration with IBM's Power, the more I'm impressed. There's generally no real competition out there. So I will stop sharing. Abilio, we're back to you.
Thank you, Andrew. I reckon that I didn't see that there was before we go to the Q&A, we had a chat earlier this afternoon about the scale up and the scale out, and I was telling you about the management challenges, right? Because it is if you can do more with less systems, that's the benefit. Is this a fair statement to say?
Yes, as I said briefly in there, the preferred option really should always be to scale up. So we can do that in our scale out boxes as well, because we can do 4 terabytes of memory in there. You have to make a decision which memory modules you're going to go with, but we can do a quarter at a time in the same capacity. So if you started with 512 and a single socket, we can take you to 2 sockets, and so we can scale up within the box, but we can only scale up to a certain amount. If you were looking at 4 terabytes, in all honesty, I would point you at the 950 because that's a 4-socket machine and it scales to 16. So once we scale up, rather than bring another platform in, it's a reliability thing as well. It's statistically, if something is 99.5% reliable, for example, and so that's what one box can do, and you get 2 of them, well, the reliability of the pair actually goes down because you only have 99.5 times 99.5. So the more systems you find, and we find this with huge VMware farms, the more systems you have, the more frequently you'll have a system that's down and needs attention. Right. So less is more.
Okay, awesome.
As we don't have to manage as many physical platforms. We don't take up the real estate, which is the important thing. I had a client here in New Zealand who was looking at HANA when we still sold System X, and we'd sold them a System X platform, and they were looking at going to HANA for the whole business, changing from R3, and they needed something in the order of 4 terabytes, and And at the time, the biggest box that would work for business warehouse was a terabyte. So, and we had to cluster them. We have to cluster them, and each of these boxes was 8U in size. And so you had to, well, we want 4 terabytes, so we've got to buy a minimum of 4. Then we've got a hot spare, which is 5. And then we do the same again for ECC. So that's 10. That's 80U. That's 2 racks.
Okay. Mm-hmm.
These guys, were pretty full. So to expand another rack in their computer room was going to cost them $500,000. A power solution, which was running on an 880, we bought it with 9 terabytes to start with, was 22U.
Wow, less than a half of a rack. Yeah.
Half a rack, 5 4s. Yeah, 4 5s. 4 5s, and 2U for the controller. Absolutely, 22U. Yeah. And we can do all 9 terabytes in there. In fact, we've expanded that to 11. So we have a
I can imagine the savings on energy as well, and heating as well. So cooling.
Well, heating. Everybody forgets about heating and cooling. Those BTU heat output. For every server you drop in there. I mean, yes, certainly, power processors do run hot, but you get more work per BTU, shall we say. Right? We actually do a lot more work for the amount of heat that we generate compared to Intel. So all of these things added up to an improved TCO. Don't just look at the TCA, right? Don't look at just the acquisition cost when Dell come in and say, here, this is the special for the week, or HP or whomever. Don't just look at that. Look at the IBM systems. We actually are very competitive. And that's why, to some extent, we went in with industry standard RAM to try and lower the costs on our smaller boxes. So I hope
let me jump. Yeah, let me jump on the QA very quickly. Some comments on the Q&A, saying that you don't have a good site, Andrew, and we all know that. Some recommendations for the name. So X using Roman numeric, and there's a question here. So Andrew, where do you recommend performance mode in a 24/7 enterprise environment? I reckon. Is that the question?
So where do I recommend?
Where do you recommend?
Yeah. The performance
mode. Yeah. In a 24/7.
Maximum. Yeah. Well, as I say, all our systems ship with that on by default. So we will actually run that processor as fast as we can for as little time as possible to try and get as much workload through as possible. So if you need performance on your system, absolutely. So if your systems are really busy, and I was just trying to think, if I go back to this, that's the inverted triangle, when there aren't very many spare cycles. So we try and knock them off as fast as possible, right?
Okay.
If you've got a very light application and you've got plenty of time and lots of inactive cycles, then you could go to the dynamic mode. So by default, our systems come, but we just want to make people aware that they can actually do things. They can save energy if they want to.
Yeah. Okay. That's pretty good. I reckon that's it. Mr. Benjamin Kwan, he was complaining that I didn't allow him to go as a panelist. So, did you wanna add any comment, Ben? Just so you guys know, Benjamin Kwan is the sales leader for power and mainframe for New Zealand. So, can you wanna do a comment, like 2-3 minutes? We are running a bit rather out of time, so.
Yeah, look, thanks. I don't really have much to add on that extremely comprehensive presentation. It was a really good summary, Andrew. So just going back to what Andrew said about the extra performance capability, if you combine all those different factors together, especially the way that the likes of AWS and Azure currently charge you in terms of the threading and compared to the power cores. For example, an interesting article in LinkedIn from the technology officer out of IBM in the UK. He runs the power systems business there. He sort of summarized that quite well in an article where he mentioned that by using Power on-prem or in your private cloud, you could run, for example, any of the IBM cloud packs based on Red Hat for up to a sixth of the price compared to the cloud, simply from the consolidation of the workloads and the way that the licensing models work. So that's the kind of money savings you get. And of course, on the x86 platform you're running, the utilization capability is never very good. The typical utilization, 30-40%. They always overspec the system so that to cope with the maximum potential workloads, which hardly customers hardly ever achieve the maximum workload, and it's never consistent. There's odd peaks where you get maximum workload, but on the Power Platform, because our secret sauce is the virtualization capability, we can combine all those workloads on the same server and consistently achieve 80-85% utilization, and that's another just another one of those nice features we have that help customers save a lot of money.
Yeah, it's kind of along the line of we do twice as much per core, and we can do more with fewer cores as well. So absolutely, run our processors up. I had a customer ring me and said, my processor is running at 100% since I've done this. And I went, fantastic. And he went, no, that's bad. And I went, no, it's not. It means your machine's got enough work for it to do. And yeah, it's fine. These things work very hard.
Yeah, I'll just finish off with one example that we, with a customer that we won against a number of x86 competitors last year. And we talk about SAP and SAP HANA workloads a lot because that exemplifies the capabilities that Power is capable of. But in this particular customer, they had 28 servers across 7 different sites, utilizing over, I think it was 2,100 x86 cores. We consolidated that down to 2 E90 systems running 192 cores, and not to mention the reduced costs around the networking infrastructure, the storage infrastructure, all the interconnect, less intrusion points around the networking, so the security costs went down. And the cost on the hardware was within a 10% differential to the x86 in terms of the servers, yet the savings from not having to spend money on, I think it was a dozen networking switches, all the SAN switches, over 7 SANs across the 7 different sites, all that down to 2 Power systems and 2 IBM Flash systems. And there was just a massive savings. On a more realistic scale, in terms of New Zealand business size, we last year we also won once again another SAP HANA. This customer had 2 terabyte database, and we basically were competing against another green vendor, a green colored vendor. Our solution was ended up being 10U, I believe, because it was a 1 server, 1 SAN, and 1 switch. Compared, and that's basically 10U versus HP's equivalent solution of 1.5 rack. Sorry, I did let that green vendor slip. I couldn't help it.
Yes, and you're giving away half our presentation for next week.
Yeah, sorry about that. But let's just give an example of the consolidation and virtualization capability.
That's a good point. That's a good point. Can I wrap up?
I think so. Thank you very much, ladies and gentlemen, for paying attention.
So thank you, Andrew, and that was awesome. I just share on the chat the public folder where we are uploading the decks. So Andrew G will be uploading these decks as well to this folder. So make a good usage of it. I'm uploading the video of this recording as well, and as I said, it is a big file, so don't bother of downloading it. I will put it on my YouTube channel so you guys can take a look and replay lots of time and see what is the best size of Andrew G, and you can tell him later. Okay, don't forget to do the survey. We are ready from the first session to this session. We pick some advice and we improve it a little bit more. And if you do the same now, we will do another iteration, and in the next session we will be better than we are today. So thanks for attending this call, and see you next week, every single Wednesday at 4 p.m. Kia kaha mā te wā.